In this module, we talk about phase changes and heating curves. So going from a solid to a liquid or the other way, or from a liquid to a gas or the other way, something like that. So this is a heating curve, and what this does is a graph of temperature versus time as you take, well, you can start anywhere on this graph. Let's start from the beginning. We take a solid at some temperature below its melting point. So if this were water, this temperature here would be 0 degrees Celsius. This temperature is its boiling point. This would be 100 degrees Celsius. So we start at some temperature lower than its melting point, and we add thermal energy to it over time. So what's going to happen is, at first, the solid will warm up until it gets to its melting point. But once it reaches its melting point, as you add more energy to it, the temperature stays constant as the solid melts. So right here at the beginning of this flat portion of the curve, it's all solid at its melting point. As you add energy, some of it becomes liquid, there's still some solid, and it's an equilibrium between the solid and the liquid until you reach point B here. Right here, it's all liquid, still at the temperature of its melting point. So this is water, this is 0 Celsius still here. Then, as you add more energy, the temperature of the liquid increases until you get to its boiling point, 100 Celsius if it's water. As you add more energy, the liquid boils, becomes vapor. Again, at point C here, it's all liquid at 100 Celsius. As you add energy, there's an equilibrium between the liquid and the gas phase, until you get to point D, where now it's all gas, all vapor at the temperature of its boiling point, 100 Celsius if it's water. Then, if you add more energy, the temperature of the gas starts increasing. So what we're going to do is we're going to calculate how much energy it takes to go through these different portions of this heating curve. And the way to remember it is that if it's a flat line, no slope, you're going to use what's called the heat of fusion if it's going from liquid to solid or the other way, or heat of vaporization, delta H of vaporization, if it's going from liquid to a gas or the other way. If it's a sloped portion of the graph where there's a non-zero slope, then you're going to use Q equals mass times specific heat times delta T. And the thing that's going to change here, the mass is going to stay the same. We're not going to change the mass. But you have to remember that the specific heat of a solid is different than the specific heat of the liquid of the same substance, which is different than the specific heat of the vapor of the same substance. And delta T is going to be different depending upon where you are in this graph. So for each of these sloped portions, we're going to use Q is the amount of thermal energy that you have to put in to go, to increase the temperature, and it's going to be ms delta T. For each of the flat portions, it's going to be Q is equal to either delta H of fusion, if it's going from liquid to solid, times the amount, I'll call it M for mass. Over here, it's going to be Q is equal to mass times, let's write it the other way. It's going to be delta H of vaporization times the mass. All right, so just remember how you calculate Q for each portion of this graph. So let's do an example. So we're going to take some ice we're going to take 314.1 grams of ice, and we're going to start at temperature below its melting point, negative 27.23 degrees Celsius. We want to convert it to steam at 114.13 degrees Celsius. We want to know how much energy it takes in kilojoules to do this. Information that you need to know: the specific heat of the ice, specific heat of, the liquid, but you know that it's water, so it's 4.184 joules per gram degree Celsius. Specific heat of the steam, which is different. The heat of fusion, or delta H of fusion of the ice, and the delta H of vaporization. These numbers right here, they represent the delta H of fusion is how much energy it takes to melt 1 gram. Sometimes you see this in joules per mole. That'd be how much energy it takes to melt 1 mole of ice. Same thing for here. This is how much energy it takes to convert 1 gram of liquid water to 1 gram of gaseous water at its boiling point. So all we do is we take each section of that graph separately. Q1, Q2, Q3, Q4, and Q5. Let's go back over here. Q1 will be this region right here. Q2 will be melting it. So Q1 is raising the temperature of the solid. Q2 is how much energy to melt it. That's here. Q3 would be raising the temperature of the liquid. That's here. Q4 would be vaporizing it. And Q5 would be heating up the steam. So for Q1, we're going to use ms delta T. For Q2, delta H of fusion times the mass. Q3, ms delta T. Q4, delta H of vaporization times the mass. And Q5, ms delta T, where the S is different here, here, and here. So let's plug those numbers in. Pause this and check out all the numbers here, but this is where all the numbers go. And what I've done, I've gotten the answers for each section of the graph in joules, and I kept the same power of 10 so we could know where to round off in terms of sig figs. It ends up that we're going to end up adding all these numbers, and when it's times 10 to the 4th joules, it's 2 places past the decimal is the least precise, so we'll keep that. So make sure you know where everything is. So this is the mass of the ice, specific heat of the ice. Delta T of the ice is final, which is 0 minus the initial negative 27.23, so negative is a positive. You get this. To melt it, delta H of fusion times the mass. To raise the temperature of the water, mass times the specific heat of liquid water, which you're supposed to know, times the delta T of the water, which is a final, which is 100 Celsius, minus the initial, 0. Not minus 27.23, but just from after we've already melted, 0. And then to vaporize it, delta H of vaporization times the mass. And to raise the temperature of the steam, mass times the specific heat of the steam. Now delta T of the steam is the final, which is this, minus the initial temperature of the steam, which is its boiling point. We get that. So we add up all these guys, get 97.31 times 10 to the 4th joules, which converts to be 973.1 kilojoules.